Look up at the night sky, away from the city lights, and you'll see it, a faint, hazy band of stars stretching from one horizon to the other. That's our home, the Milky Way. But if you could travel far beyond it, you might catch a glimpse of something even more spectacular, the Andromeda Galaxy, a swirling colossus of over 1 trillion stars, hanging in the void like a silent, spinning jewel. Have you ever wondered how something so immense, so beautiful, so impossibly grand could even exist? How did these islands of stars, these galaxies, come to be? The story of galaxy formation is one of the most extraordinary journeys in all of science, a tale of chaos and creation, of gravity and time, of darkness and light. It's a story that begins just after the birth of the universe itself, and it's still unfolding all around us, right above our heads. Today, we're setting off on a voyage through that story. We'll explore 30 fascinating facts about galaxy formation and evolution facts that will completely reshape how you see that starry canvas each night. From the faintest dwarf galaxies barely holding themselves together to the supermassive black holes lurking at the hearts of giants, every fact reveals another layer of this cosmic masterpiece. You'll learn how galaxies collide and merge, how they grow, change, and sometimes even fade away over billions of years. This isn't just a list of trivia, it's an invitation to see the universe differently, to understand our place within it on a deeper level. So get comfortable, open your mind, and let's embark on this journey together. By the end of this video, the night sky won't just be a scattering of lights, it will be a living, evolving story, and you'll know exactly how to read it. To understand how galaxies came to be, we have to rewind the cosmic clock almost all the way back to the very beginning. Picture this, a moment just after the Big Bang. The entire universe we know, every star, every planet, every single thing was compressed into a space smaller than a single atom. It was an environment of almost unimaginable energy and heat, a super hot, super dense primordial soup. For hundreds of thousands of years, the universe was too hot for atoms to even form. It was just a swirling, chaotic sea of fundamental particles like protons, electrons, and photons, all bouncing off each other in a brilliant, opaque fog. There were no stars, no planets, and certainly no galaxies. In fact, this early universe was almost perfectly smooth, a nearly featureless expanse of energy. If you could have looked across the cosmos back then, it would have seemed remarkably uniform, the same in every direction you gazed. This incredible smoothness is a key piece of the puzzle, because it's from this state of near-perfect uniformity that all the vast structures we see today would eventually emerge. The stage was set, but it was utterly blank. So how did we get from that featureless beginning to the intricate cosmic web of galaxies we see today? The answer lies in the tiniest of imperfections, microscopic seeds planted in the fabric of space-time itself. During an even earlier period of rapid expansion called cosmic inflation, tiny quantum fluctuations, minuscule ripples in energy that pop in and out of existence at the subatomic level, were suddenly stretched to enormous sizes. These tiny wrinkles in the early universe became the blueprints for everything. They were the places where, just slightly, the density of matter was a little bit higher than the areas around them. And in a universe governed by gravity, even the smallest over-dense region has a gravitational advantage. Over astronomical amounts of time, gravity would relentlessly pull matter toward these slight density variations, gathering more and more material, building the first structures, and eventually leading to the magnificent galaxies we observe. That faint, hazy band of the Milky Way we see today, and the trillion-star wonder of Andromeda, all owe their existence to those infinitesimal quantum ripples, magnified to a cosmic scale. But for those tiny density variations to grow into the galaxies we see, they needed a powerful, unseen ally, an invisible force that provided the cosmic scaffolding for everything we can observe. That force is dark matter. We can't see it, we can't touch it, and we've never directly detected it in a lab, yet it makes up roughly 85% of all the matter in the universe. Its presence is only betrayed by its immense gravitational pull. In the early universe, while normal matter, the stuff that makes up stars, planets, and us, was still a hot, pressurized plasma, dark matter was already cold and sluggish, unaffected by the intense radiation pressure that prevented atoms from clumping together. This gave it a huge head start. The gravity from these dark matter concentrations began to pull in everything around them, carving out vast gravitational wells in the fabric of space-time. Think of it like this: if the universe were a flat, taut rubber sheet, dark matter would be like placing heavy, invisible weights on it, creating deep dimples. Then, as the normal matter cooled and settled after the formation of the first atoms, it simply flowed down into these pre-existing gravitational basins, pooling and condensing, ready to ignite into the first brilliant stars. Without this dark matter framework, the pull of gravity from ordinary matter alone would have been far too weak to overcome the universe's rapid expansion. Galaxies as we know them might never have formed at all. So every majestic spiral and every glowing elliptical galaxy we see is really just the visible tracer of a much larger, much more massive and utterly invisible halo of dark matter, the true hidden architecture of the cosmos. From those immense cosmic foundations built by dark matter, the very first galaxies began to take shape. It's a humbling thought, but the grandest structures in our universe had remarkably humble beginnings. These pioneering galaxies started forming only a few 100 million years after the Big Bang, emerging from the fading glow of the cosmic dawn, and by today's standards they were incredibly small. We're not just talking a little bit smaller than our Milky Way. These first galactic building blocks were often just 1,000th of its mass. To put that into perspective, if our galaxy were a full-grown blue whale, these first galaxies would be about the size of a newborn dolphin. They weren't the magnificent spirals or stately ellipticals we see today. They were essentially cosmic seeds, tiny, irregular clumps of gas and dark matter, each containing perhaps only a few million or billion stars. But what they lacked in size, they more than made up for in significance. Within these fragile, nascent structures, a monumental revolution was taking place, the birth of the very first stars. This was the end of the cosmic dark ages, a period when the universe was a vast, empty, and unlit expanse. These first stars, often called population 3 stars, were unlike anything that exists today. They were behemoths, giants that could be hundreds of times more massive than our Sun, and they burned ferociously hot and bright, living fast and dying young in spectacular supernova explosions. Their intense ultraviolet radiation began to tear apart the neutral hydrogen atoms that filled space, a process known as reionization, which fundamentally changed the nature of the entire universe, making it transparent to light and allowing future galaxies to be seen. The powerful blasts from their deaths enriched the surrounding gas with the first heavy elements, the carbon, oxygen, and iron that would one day become the building blocks of planets and life. So while these first galaxies were tiny, they were the crucibles of creation, the workshops where the first complex chemistry of the cosmos began. They were the pioneers that lit the first candles in the darkness, their collective glow beginning to etch the outlines of the cosmic web that would define the universe for billions of years to come. As the universe aged and these first tiny galaxies began to populate the cosmos, a new, more violent phase of galactic life began. The serene, almost peaceful image we have of galaxies slowly spinning in the void is in many ways a beautiful illusion. The true story of how galaxies grow into the majestic giants we see today is one of relentless cosmic consumption, a process astronomers vividly term galactic cannibalism. It turns out that the primary way a large galaxy like our Milky Way gains mass and grows isn't just by passively collecting gas to form new stars. It's by actively devouring its smaller galactic neighbors. This isn't a rare or exotic event. It's a fundamental aspect of galactic evolution happening all across the universe. We are, in fact, living in the midst of such an event right now. Our own galaxy is currently in the process of consuming a much smaller companion known as the Sagittarius dwarf spheroidal galaxy. This tiny galaxy, containing only a few tens of millions of stars, has been caught in the Milky Way's immense gravitational pull. Over billions of years, it has made multiple passes through the plane of our galaxy, and with each orbit, our galaxy's tidal forces have stretched and torn it apart, pulling stars from its grasp and incorporating them into the Milky Way's outer halo. If you could speed up time, you would see this dwarf galaxy not as a distinct object, but as a long, shimmering river of stars, a stellar stream wrapping around our galaxy like a faint cosmic ribbon. This stream is the direct evidence of the digestion process, the scattered crumbs from a galactic meal that's still ongoing. The stars from Sagittarius are being assimilated, becoming forever a part of our own galaxy's structure. This process demonstrates that galaxies are not isolated islands but dynamic ecosystems where the strong gravitationally dominate the weak. And the future holds an event of an entirely different scale, one that will redefine our night sky and the very structure of our galactic home. In approximately 4.5 billion years, the Milky Way is set to experience not a meal, but a merger with an equal. Our largest galactic neighbor, the Andromeda Galaxy, is hurtling towards us at a speed of around 110 kilometers per second. This isn't a random catastrophe. It's a gravitational inevitability, a cosmic dance that has been preordained since these two giants first formed. When we imagine this collision, it's natural to picture a violent, fiery crash, but the reality is both more spectacular and far less destructive than it sounds. The vast distances between stars mean that actual stellar collisions are incredibly unlikely. Instead, the merger will be a slow, graceful gravitational interaction, a billion-year-long tango of two immense spirals. In the first phases, as Andromeda fills our night sky, the gravitational forces will begin to warp and distort the beautiful spiral arms of both galaxies, pulling out long tails of gas and stars. They will swing past each other, then fall back together, their mutual gravity ensuring they eventually coalesce into a single, new galaxy, most likely a large, featureless elliptical galaxy that astronomers have nicknamed Milky. Within this new structure, the stellar populations of both the Milky Way and Andromeda will be thoroughly mixed. Our solar system will likely be flung into a much wider orbit, but it will probably survive the upheaval physically unscathed. This grand merger is the ultimate expression of galactic cannibalism, where two giants combine to create something new. It's a process of destruction that leads to creation, as the collision will trigger a massive burst of new star formation, lighting up the cosmos with the birth of billions of new stars. This event, witnessed across the universe, is how galaxies mature and evolve, growing not just in silence but through magnificent and transformative encounters. This brings us to one of the most beautiful and enduring mysteries of galactic structure, the majestic spiral arms themselves. For a long time, astronomers were puzzled by these elegant features. If a galaxy is simply a disk of stars rotating around a central core, then a simple law of physics should cause the spiral arms to wind up tighter and tighter over time, eventually blurring into a featureless disk. The outer stars orbit more slowly than the inner stars, so any fixed structure would be stretched and smeared out over a few 100 million years, a blink of an eye on the cosmic timescale. Yet we see spiral galaxies billions of years old with their arms still clearly defined. The solution to this puzzle is as elegant as the spirals themselves. The arms are not permanent structures made of the same group of stars like a frozen pinwheel. Instead, they are what scientists call density waves, dynamic patterns that move through the galactic disk. Imagine the wave that fans create in a sports stadium. The wave travels around the arena, but the people themselves only stand up and sit down. They don't all move with the wave. In a galaxy, the spiral arm is that traveling wave of compression, and the stars and gas are the fans. As this density wave moves through the disk, it compresses the vast clouds of interstellar gas and dust it encounters, much like a traffic jam on a highway compresses cars. This compression is the trigger for star birth. The increased pressure forces pockets of gas to collapse under their own gravity, igniting into brilliant, hot young stars. This is why the spiral arms appear so bright and blue. They are lined with these short-lived, massive newborn stars that illuminate the wave front, but the individual stars themselves are not permanently tied to the arm. They orbit in and out of these patterns over millions of years. A star will enter a spiral arm, spending some time within this crowded, star-forming region before its orbit carries it out the other side into the more sparsely populated spaces between the arms. Our own Sun, for instance, has likely passed through several of the Milky Way's spiral arms during its lifetime, each passage a potential period of increased comet activity and stellar encounters that may have influenced the history of our solar system. This elegant mechanism solves the winding problem perfectly. The pattern persists for billions of years, continually triggering new rounds of star formation and creating one of the most iconic and breathtaking sights in the entire universe. Now, if the spiral arms are the bustling stellar nurseries of a galaxy, then the very center is its ancient beating heart. And for nearly every large galaxy we've observed, that heart is not just a dense cluster of stars, but a supermassive black hole. These are not the black holes formed from the collapse of a single massive star. Those are mere infants in comparison. A supermassive black hole is a cosmic monster of almost incomprehensible scale, with a mass millions or even billions of times that of our Sun, all crushed into a region of space smaller than our solar system. Their existence was once purely theoretical, but we now know they are not rare anomalies. They are a fundamental feature of galactic architecture. Our own Milky Way hosts one such behemoth, a dark titan known as Sagittarius, a star. Though it is hidden from our view by thick clouds of interstellar dust, we can track the frantic orbits of stars around it, tracing paths that reveal the presence of an invisible, immense gravitational anchor. From their motions, we've calculated that this silent giant holds the mass of 4 million suns, all confined to a point from which not even light can escape. The most fascinating aspect of these cosmic leviathans is not just their terrifying power, but the intimate and dynamic relationship they seem to share with their host galaxies. For decades, astronomers wondered if a galaxy's overall size and the mass of its central black hole were connected, and the answer has proven to be a resounding yes. There is a remarkably tight correlation between the two. Larger galaxies with more massive stellar bulges almost invariably harbor larger supermassive black holes. This strong link suggests that the growth of the black hole and the growth of the galaxy itself are deeply intertwined, a process known as co-evolution. They didn't just happen to form in the same place. Their histories are fundamentally braided together, each influencing the other's development over billions of years. This co-evolution is governed by a powerful and complex process called feedback. For a long time, it was a puzzle. If gravity is constantly pulling vast reservoirs of gas into the center of a galaxy, why doesn't all that fuel simply collapse into a frenzy of new star formation, creating a dazzling but short-lived stellar metropolis? The answer lies with the black hole. While a supermassive black hole is the ultimate consumer, it is also a tremendous regulator. As enormous amounts of gas and dust spiral inward in an accretion disk, they are heated to incredible temperatures, releasing a blinding amount of radiation. But sometimes the black hole doesn't just consume quietly. It can unleash titanic outbursts of energy. These active phases, when the black hole is termed a quasar or an active galactic nucleus, can drive powerful winds and jets of material shooting out across the galaxy at nearly the speed of light. This incredible outpouring of energy acts like a cosmic thermostat. It violently heats up and disperses the surrounding reservoirs of cold gas, the very raw material needed to form new stars. By doing so, it effectively shuts down or quenches star formation in the galaxy's central regions. This feedback process prevents the galaxy from either turning all of its gas into stars too quickly or from funneling too much material onto the black hole itself. It's a self-regulating cycle, a delicate dance of creation and destruction. The black hole's violent output ensures that it doesn't grow too powerful for its own good, while also preventing the galaxy from burning too brightly and too fast. In this way, the supermassive black hole, though hidden in darkness, is one of the key architects of its galaxy's destiny, shaping its structure and controlling its growth from the shadows. Just as a tree's rings record its history of growth and drought, a galaxy's color is a direct, luminous readout of its evolutionary story. If you were to take a vast cosmic census cataloging galaxies by their hue, you would quickly notice they don't come in every shade of the rainbow. Instead, they fall into two dominant camps, a vibrant, brilliant blue and a deep, somber red. This isn't a random artistic choice by the universe. It's a fundamental diagnostic tool, a color code that tells us precisely what a galaxy is doing and what stage of life it's in. The secret to this color code lies in the types of stars that dominate a galaxy's light. Blue galaxies are the cosmic powerhouses, the bustling metropolises of star formation. Their intense blue glow comes from an abundance of massive, hot, young stars. These stellar behemoths burn their nuclear fuel at a ferociously rapid rate, shining with a brilliant blue-white light and living for only a few tens of millions of years, a mere blink in cosmic time. Their very presence is a smoking gun, telling us that the galaxy is rich with cold gas and that the process of gravitational collapse into new stars is happening vigorously right now. When we look at a galaxy like the iconic Whirlpool Galaxy with its vivid blue spiral arms, we are essentially seeing a map of its active stellar nurseries. In stark contrast, red galaxies are the cosmic retirement communities. Their ruddy glow signals a population of older, cooler stars. The massive blue stars that once lit up these galaxies have long since burned out in spectacular supernova, and no new stars are being born to replace them. What remains are the smaller, longer-lived stars like red dwarfs and red giants, which can shine steadily for trillions of years. Their light is cooler and redder, and without any new blue stars to balance the palette, the entire galaxy takes on a reddish hue. This transition from blue to red is one of the most significant phases in a galaxy's life, marking the point when its star-forming days are essentially over. But what causes this shutdown? The reasons are varied and often brutal. A galaxy might simply use up its reserves of cold gas, the raw fuel for star birth. More dramatically, its gas could be violently stripped away during a collision with another galaxy, or as it plows through the superheated plasma that fills galaxy clusters. Or, as we learned with supermassive black holes, intense feedback from an active galactic nucleus can heat and disperse the gas, preventing it from ever cooling down enough to collapse into new stars. This cosmic color code is more than just a pretty observation. It's a key that allows astronomers to take a single image of thousands of galaxies and immediately understand their demographics, which are young and vibrant, which are old and fading, and how the population of the universe as a whole has changed over its 14 billion-year history. This process of cosmic enrichment and recycling finds one of its most spectacular expressions in a phenomenon known as a galactic fountain. We often think of a galaxy as a flat, spinning disk, but its ecosystem extends far above and below this central plane into a vast, gaseous halo. The engine that drives material up into this halo is the incredible power of supernova explosions. When a massive star reaches the end of its life and explodes, it does more than just scatter its elemental ashes into space. It creates a powerful shockwave that can blow a gigantic bubble in the surrounding interstellar gas. Imagine the aftermath of a tremendous underwater volcanic eruption, where a colossal plume of heated material and bubbles violently surges toward the surface. In a galaxy, that eruption is a supernova, and the plume is a hot, expanding superbubble of million-degree gas thrusting upwards out of the galactic disk. These immense structures can loft enormous quantities of gas, enough to form millions of stars high above the galaxy's plane, sometimes reaching distances of thousands of light years. From our perspective within the Milky Way, if we could see these fountains in action, they would appear as towering, shimmering pillars of energized gas, arching over the disk like celestial waterfalls in reverse. But what goes up must eventually come down. As this hot gas travels through the halo, it gradually radiates away its tremendous heat and energy. It begins to cool down and condense into denser clouds. Eventually, pulled by the galaxy's relentless gravity, these now cooled clouds of enriched gas begin to fall back down toward the disk, plummeting through the void like a spectacular rain of star-making material. This returning rain is not the same pristine hydrogen and helium that was blown out. It is now heavily salted with the heavy elements forged in the heart of the exploded star and churned up by the explosion itself, elements like oxygen, silicon, and iron. When these metal-rich clouds crash back into the galactic disk, they seed the interstellar medium with the very ingredients needed to form rocky planets and ultimately life. This magnificent cycle of explosion, ejection, cooling, and return ensures that a galaxy doesn't simply blow its valuable raw materials out into intergalactic space forever. Instead, it continuously recycles them. Each new generation of stars is born from gas that is slightly more enriched with heavy elements than the last, allowing for the formation of more complex planets and paving the way for the incredible diversity of worlds we now observe throughout the cosmos. The galactic fountain is the galaxy's own sustainable system, a beautiful mechanism of death and rebirth that turns the catastrophic end of stars into the promise of new beginnings. While the majestic swirl of stars and gas we see in a galaxy like our own is breathtaking, it represents only the shimmering tip of a much larger and profoundly more massive cosmic iceberg. The true bulk of a galaxy's substance, the very foundation of its immense gravitational pull, exists in a form we cannot see, an enormous, diffuse sphere of dark matter called a galactic halo. To grasp the sheer scale of this hidden architecture, let's consider our own Milky Way. The bright, star-filled disk that we observe stretching across the night sky is roughly 100,000 light-years from end to end. That's an almost unimaginable distance, but the dark matter halo that cradles our galaxy is truly colossal, extending out to nearly 1 million light-years from the center. This means the invisible component of our galaxy is about 10 times wider than its luminous stellar disk. If we could see the full extent of the Milky Way's dark matter halo in the sky, it would appear larger than the constellations of Orion and the Big Dipper combined, a faint, gargantuan sphere enveloping everything we know. But it's not just the size that's staggering, it's the mass. While the halo is incredibly diffuse, its vast volume means it contains an overwhelming majority of the galaxy's total substance. Astronomers estimate that for every pound of ordinary matter, the stuff that makes up every star, every planet, and every one of us, there is roughly 6 pounds of dark matter holding it all together gravitationally. This invisible material provides the essential scaffolding upon which the visible galaxy is built. Without the immense gravitational well carved out by this dark matter halo, the rapid rotation of the galaxy's outer stars would literally fling them off into the emptiness of intergalactic space. The fact that these distant stars orbit at such high speeds without escaping is one of the primary pieces of evidence for dark matter's existence. There simply isn't enough visible mass in the entire disk to hold them in their orbits. The halo is the unseen anchor, the gravitational glue that keeps the entire majestic structure from flying apart. This concept transforms our understanding of a galaxy's boundaries. We often picture a galaxy as a discrete island of light, but in reality, the edges of these dark matter halos are so vast and fuzzy that they actually overlap with the halos of neighboring galaxies long before the visible parts ever get close. Our Milky Way's halo is already gently brushing up against the halo of the approaching Andromeda Galaxy, their invisible matter beginning to interact billions of years before their stellar disks will ever meet. This shadowy interplay is the first subtle step in the grand cosmic dance of a future galactic merger, all happening unseen in the dark spaces between the stars. Zooming out from the life cycle of individual galaxies reveals a pattern of such immense scale and beauty that it redefines our understanding of the universe's structure. If you could view the cosmos from a God's eye perspective, you would not see galaxies scattered randomly like tossed salt across a dark tablecloth. Instead, you would witness an architecture of breathtaking complexity, a vast three-dimensional cosmic web. This web is the largest known structure in existence, a delicate lattice of glittering filaments and dense nodes, all surrounding unimaginably empty, dark voids. This isn't a metaphor, it's the actual large-scale structure of the universe, a spider's silk of galaxies spun across billions of light years. The galaxies we've been discussing are not isolated islands at all. They are the luminous trace elements, the shining dots that outline this grand design. They cling to the dense filaments like dew on a spider's web, and they crowd together at the intersections of those filaments in massive, gravitationally bound cities known as galaxy clusters. These clusters are the true titans of the cosmos. A single cluster can contain anywhere from hundreds to many thousands of individual galaxies, all swarming around a common center of gravity. But the galaxies themselves are only a small part of the story. For every ounce of visible matter in those galaxies, there is vastly more material in the form of a superheated, thin plasma that fills the space between them. This intracluster medium is gas so incredibly hot, tens of millions of degrees, that it doesn't emit visible light. Instead, it glows brilliantly in high-energy X-rays. To our X-ray telescopes, a galaxy cluster doesn't look like a collection of points of light. It appears as a colossal, diffuse cloud of energy, a single shimmering blob of intense radiation that can outshine all the stars in all its galaxies combined. This hot gas is the primary baryonic or normal matter component of a cluster, and it tells a violent history. It was heated to such tremendous temperatures by the immense gravitational forces at work as the cluster formed. As galaxies and dark matter fell into the growing cluster, their gravitational energy was converted into this incredible heat, essentially cooking the gas to X-ray emitting temperatures. The existence of this cosmic web is a direct result of the initial conditions of the universe, a fossil relic from the Big Bang itself. The tiny quantum fluctuations in the primordial universe, amplified by gravity over billions of years, are what grew into these filaments and clusters. The dark matter, acting as the invisible scaffolding, collapsed first into a web-like structure, and the ordinary gas simply followed, flowing along the dark matter highways and pooling in the nodes to form galaxies and clusters. The voids, those vast empty regions that make up most of the volume of the universe, are the inverse of this process. They are the places where matter was scooped out, leaving behind cosmic deserts that can be hundreds of millions of light years across. This intricate pattern, this cosmic web, is the final and largest expression of gravity's creative power, a network that connects every galaxy, cluster, and supercluster into a single, coherent, and magnificent structure. While the galactic fountain represents a gentle, recycling rain of material, some galaxies experience something far more extreme, a violent, superheated hurricane that doesn't just lift gas but blasts it out into intergalactic space forever. This phenomenon is known as a galactic wind, and it represents one of the most powerful feedback mechanisms in the universe, capable of radically reshaping a galaxy's destiny. To understand the sheer force of these winds, we must visit the most intense stellar environments imaginable, starburst galaxies. These are galaxies gripped by a fever of star formation, where new stars are being born at a rate hundreds or even thousands of times faster than in our own placid Milky Way. It's a cosmic boomtown on a colossal scale, but such rapid, unchecked growth is ultimately unsustainable. The primary engine of this ferocious outflow is the collective fury of massive stars and their spectacular deaths. In these densely packed stellar nurseries, short-lived massive stars dominate. They flood their surroundings with intense ultraviolet radiation and drive powerful stellar wind streams of charged particles flowing from their surfaces at millions of miles per hour. But the real catalyst comes when these stars inevitably die. Supernova explosions erupt in rapid succession, like a string of cosmic firecrackers, each one blasting out a shockwave that heats the surrounding gas to millions of degrees and accelerates it to tremendous velocities. This isn't a gentle fountain, it's a pressure cooker with no release valve. The combined energy from thousands of these events creates a superheated bubble that eventually ruptures, punching through the galaxy's disk and erupting out into the halo. This creates a biconical outflow, a hurricane of hot gas and heavy elements shooting out above and below the galaxy at speeds that can exceed 2 million miles per hour. We can actually observe these spectacular structures in other galaxies. They appear as vast, glowing lobes of X-ray and radio emission extending far beyond the visible starlight. The consequences of this exodus are profound. This ejected gas is the galaxy's future fuel supply, the raw material for generations of stars yet unborn. By violently expelling it, the galactic wind effectively starves the galaxy. It is a self-regulating, almost paradoxical process. The very mechanism that creates a brilliant burst of new stars also shuts down the factory that produced them. In extreme cases, a particularly powerful wind can completely quench a galaxy, halting star formation entirely and consigning it to a future as a red and dead elliptical galaxy, its stellar population slowly aging with no new stars to renew its light. This dramatic feedback loop solves a major puzzle in astronomy. Why don't the largest galaxies just keep forming stars forever? They have the most gravity to pull in gas, so why do many of them become dormant? Galactic winds provide the answer. They demonstrate that a galaxy is not a closed system. It's an open one, constantly interacting with and losing material to the vast intergalactic medium. The heavy elements forged in the hearts of those massive stars, the oxygen, carbon, and iron essential for planets and life, don't all fall back down. A significant portion is lost forever, enriching the barren spaces between galaxies and seeding the entire cosmos with the building blocks of complexity. So, while a galactic wind might spell the end of star birth for one galaxy, it sows the seeds for future possibilities across the universe, a testament to the deeply interconnected nature of cosmic evolution. Now, this grand architecture of the cosmic web and the violent feedback from galactic winds all hinge on the presence of that mysterious, unseen component, dark matter. But how did we first come to realize that most of the matter in the universe is completely invisible to us? The answer lies in one of the most elegant and profound discoveries in all of astronomy, one that came from simply watching how galaxies spin. According to the well-tested laws of gravity established by Newton and refined by Einstein, a galaxy should rotate like our solar system does. The Sun, possessing the vast majority of the mass, sits at the center and the planets orbit around it. Crucially, the farther a planet is from the Sun, the slower it moves in its orbit. Mercury zips around at a blistering pace, while Neptune plods along slowly in the outer darkness. This is a fundamental rule of orbital mechanics. The orbital speed of objects should decrease with distance from the central mass. For a long time, astronomers assumed that galaxies, being vast collections of stars orbiting a common center, would behave the same way. The visible mass of a galaxy, all its stars, gas, and dust, is concentrated in the bright central bulge and the inner disk. Therefore, logic dictated that stars closer to the center should orbit very quickly, while stars out in the sparse, distant suburbs of the galactic halo should crawl along at a much more leisurely pace. But when scientists began to carefully measure the velocities of stars at different distances from the centers of spiral galaxies, they were met with a result that was both baffling and revolutionary. Instead of the expected dramatic drop-off in speed, the rotation curves the graphs plotting orbital speed against distance from the center remained stubbornly, impossibly flat. What this means is that a star located 60,000 light-years from the galactic center orbits at almost exactly the same tremendous speed as a star just 10,000 light-years out. This was a direct violation of the predictions based on the amount of visible matter. If what we see is all there is, those outer stars should be moving so slowly that the galaxy's own gravity wouldn't be strong enough to hold them in orbit. They should have been flung off into the void eons ago. The only possible explanation was that there must be a tremendous amount of additional mass that we cannot see, mass that isn't concentrated in the bright center, but is instead spread throughout a vast spherical halo enveloping the entire visible galaxy. This invisible mass provides the extra gravitational grip needed to whip those distant stars around at such high speeds without letting them escape. This was the first direct observational proof of dark matter, a discovery that forced us to completely rewrite our understanding of what a galaxy actually is. The beautiful spiral we see is merely the luminous tip of a much larger, darker iceberg, forever held in the embrace of an unseen giant. This incredible journey of discovery, from mapping the invisible dark matter halos to witnessing the cosmic web itself, all stems from our ability to observe and interpret the light from galaxies. But what if we could do more than just observe their current state? What if we could read a galaxy's history page by page as if it were a cosmic memoir? This is the fascinating domain of galactic archaeology, a field where astronomers become detectives of deep time, piecing together the life story of a galaxy by studying the individual stars within it. Think of our Milky Way not as a static painting, but as a living, breathing entity with a long and complex history. That history is not written down in any book. Instead, it's encoded in the motions, positions, and chemical compositions of its hundreds of billions of stars. Each star is a fossil, a celestial artifact holding clues about the conditions in the galaxy at the time of its birth. The key is learning how to read these clues. Just as geologists can determine the history of Earth's climate by analyzing ice core samples, or archaeologists can reconstruct ancient civilizations from pottery shards and building foundations, galactic archaeologists use powerful telescopes and spectrographs to dissect starlight. The most telling clue is a star's chemical makeup. In the very early universe, the only elements were hydrogen, helium, and a tiny trace of lithium, the pristine products of the Big Bang. The first stars to form from this primordial gas were therefore metal-free, composed of nothing but these basic ingredients. When those first massive stars exploded as supernova, they became the universe's first factories for heavy elements, spewing out newly forged carbon, oxygen, iron, and all the other elements that make up our world and our bodies. The next generation of stars then formed from gas clouds that were slightly enriched with these metals. Each subsequent stellar generation builds on the last, with the interstellar gas becoming more and more metal-rich over time. Consequently, a star's metallicity, the fraction of its mass that is made up of elements heavier than helium, acts as a cosmic clock. A star with very low metallicity must be ancient, born from nearly pristine gas in the galaxy's infancy. A star like our Sun, with a moderate amount of metals, is a relative newcomer, born billions of years later from well-enriched material. By measuring the metallicity of thousands of stars, astronomers can sort them by age, creating a rough timeline of the galaxy's star formation history. But the story gets even richer when you combine chemistry with motion. The Milky Way's disk is relatively flat and orderly, with stars orbiting in a coherent plane. But its halo is a different world altogether, a chaotic, spherical cloud of old stars and ancient globular clusters with wild, randomly inclined orbits. Many of these halo stars are indeed metal-poor, confirming their great age, but crucially, they don't all move randomly. Sophisticated surveys like the European Space Agency's Gaia mission, which is precisely mapping the positions and motions of over 1 billion stars, have revealed something astounding. They've found entire streams and groups of stars within the halo that are moving together in the same direction, at the same speed, and sharing the same distinct chemical fingerprint. These are the ghostly remains of smaller galaxies that were torn apart and consumed by the Milky Way billions of years ago. Their stars were not born here, they were assimilated, and they still carry the unique signature of their original dwarf galaxy home. They are the celestial equivalent of finding a piece of ancient Roman pottery in a modern London construction site, telling a story of invasion and assimilation long after the event itself. By identifying these stellar streams and groups, galactic archaeologists can now reconstruct a detailed family tree for our galaxy. We now know the Milky Way has a violent history of cannibalism, having consumed perhaps a dozen significant dwarf galaxies and countless even smaller star clusters over its lifetime. One of the most famous of these is the Gaia Enceladus sausage, the remains of a large dwarf galaxy that collided with and was utterly destroyed by the young Milky Way around 10 billion years ago. This cataclysmic merger is thought to have puffed up the Milky Way's disk and contributed a huge number of stars to its halo. Every time we identify a new stream, it's like finding another chapter in a long-lost history book, revealing another epic encounter that helped shape the beautiful spiral we call home today. This incredible transformation of a galaxy's very shape over cosmic time reveals a fundamental truth that early astronomers could never have guessed. The iconic Hubble sequence is not a gallery of fixed, eternal types, but a cosmic flipbook showing different stages in a single, continuous story of evolution. When we look at a majestic spiral galaxy today, we are not looking at a permanent structure. We are witnessing a snapshot in a billion-year-long process of metamorphosis. The journey often begins with what appears to be cosmic chaos, an irregular galaxy. These are the galactic toddlers, often small, lumpy, and lacking any defined structure like spiral arms or a central bulge. They are typically brimming with gas and experiencing furious bursts of star formation, their irregular shape a testament to their youth and the gravitational turmoil within. They haven't yet settled into a stable, rotating disk. They are still assembling themselves, often from the merger of even smaller gas clouds. But gravity is a relentless force that seeks order. Over immense stretches of time, if left relatively undisturbed, the random motions of stars and gas within an irregular galaxy will average out, and the entire system will begin to settle into a state of organized rotation. Think of it like a spinning pizza dough tosser gradually pulling a loose lump of dough into a perfect, flat, spinning disk. As the galaxy spins, centrifugal force fights against gravity, flattening the gas and stars into a thin plane. This is the birth of a spiral galaxy. Within this now stable disk, the density wave pattern we discussed earlier can take hold, carving out those beautiful, star-forming spiral arms. The central regions also become more crowded, forming a distinct bulge of older stars. This process of internal evolution, called secular evolution, slowly and steadily changes a galaxy's appearance from the inside out, refining its structure over billions of years. However, the most dramatic changes are not driven by this slow, internal settling, but by violent encounters with others. A major merger with another sizable galaxy is the ultimate cosmic makeover event. When two spiral galaxies of similar size collide, their delicate disk structures are utterly shredded and destroyed in the gravitational chaos. The orderly, circular orbits of their stars are scrambled into random, chaotic paths. The event triggers a massive burst of star formation that rapidly consumes the remaining gas, and the powerful feedback from supernova and active black holes blows away any leftover fuel. The result of this cosmic violence is not a larger spiral, but something completely different, a smooth, featureless elliptical galaxy. These galaxies are essentially the retirement homes of the universe. All of their gas has been used up or expelled. Their stars are old and red, and they have no disk structure left whatsoever. Their stars orbit the center in every direction like a swarm of bees, giving them their characteristic three-dimensional football-like shape. This reveals the true nature of the Hubble tuning fork diagram. It's not a simple classification system, it's a narrative of transformation. A galaxy can move along this sequence throughout its life. An irregular galaxy can evolve into a spiral through internal settling. That spiral can then be transformed into an elliptical through a major merger. Even elliptical galaxies can grow by cannibalizing smaller galaxies, though this doesn't change their basic structure. The morphology we see today is simply a reflection of a galaxy's most recent history, its last major interaction. A serene, grand design spiral like the Whirlpool Galaxy has likely lived a relatively quiet life, while a giant elliptical galaxy like Messier 87 in the Virgo cluster is a veteran of a violent past, its smooth appearance belying a history of colossal collisions that shaped its present form. For hundreds of millions of years after the Big Bang, the universe was a profoundly different place, not a sparkling starscape, but a silent, featureless fog. This was the cosmic dark ages, a time when space was filled with a thick, neutral hydrogen gas that absorbed light, rendering the entire cosmos completely and utterly dark. There were no stars, no galaxies to be seen. If you could have been there, you would have been blind, surrounded by an impenetrable gloom. But this darkness was not destined to last forever. The ending of this epoch, a period astronomers call the epoch of reionization, was one of the most important and gradual transformations in cosmic history. It was the moment the universe turned on the lights. This dawn was not a single, sudden event like flipping a switch. It was a slow, persistent process that unfolded over several 100 million years, a drawn-out cosmic sunrise driven by the first emerging structures in the universe. The key players were the first generations of stars and galaxies, along with the incredibly bright and powerful quasars, active supermassive black holes at the centers of some of those early galaxies. These objects began pouring torrents of high-energy ultraviolet radiation out into the surrounding darkness. This intense UV light was the catalyst for change. It worked like a cosmic ultraviolet laser, striking the countless neutral hydrogen atoms that filled all of space. A neutral hydrogen atom is simply a single proton orbited by a single electron. The radiation from these first luminous objects was so energetic that it could blast that electron right off the atom, a process known as ionization. One by one, atom by atom, these bubbles of ionized, transparent plasma began to form around each of these early sources of light. Imagine a cold, foggy morning where you can only see a few feet in front of you. Then a single, powerful lamp turns on, and its heat begins to burn off the fog immediately around it, creating a small clearing. Then another lamp turns on, and another, each creating its own little bubble of clear air. Over time, these bubbles grow larger and begin to overlap and merge until eventually the entire fog bank has dissipated, revealing a clear sky. That is precisely what happened on a cosmic scale. For millions of years, these isolated bubbles of clarity grew steadily around the first galaxies and quasars. The process was slow and patchy, not uniform. Some regions of the universe, rich with early galactic activity, became transparent first. Other, more quiet regions remained shrouded in the neutral hydrogen fog for much longer. It was a cosmic game of connect the dots played out over an unimaginable time span. This gradual ionization was what ultimately made the universe transparent to light, allowing the photons from all subsequent generations of stars and galaxies to travel across billions of light years without being absorbed, finally making the universe observable. The faint, ancient light from some of the very first galaxies that helped cause this reionization is what our most powerful telescopes, like the James Webb Space Telescope, are now detecting and studying. We are essentially looking back in time to witness the final moments of the cosmic dawn, watching as the last patches of that primordial fog were finally burned away, forever revealing the brilliant and star-filled universe we are part of today. While the graceful spiral arms of a galaxy capture our attention, there's another internal structure at work that plays a far more active role in shaping its destiny, the galactic bar. Not all spiral galaxies have them, but a majority do, including our own Milky Way. If you could view our galaxy from above, you'd see this bar not as a solid object, but as a dense, elongated lane of stars, gas, and dust cutting directly through the central bulge like the straight bar of a celestial dumbbell. This isn't a static structure, it's a dynamic engine, a massive gravitational mechanism that acts as the galaxy's chief traffic controller for interstellar gas. The bar rotates as a single, rigid unit, and its immense gravitational pull creates powerful forces that orchestrate the flow of material across vast distances within the galaxy. Think of the bar's gravitational field as creating a kind of cosmic conveyor belt. As it rotates, it effectively herds the gas that resides in the outer regions of the galactic disk, pulling it inward from the spiral arms and funneling it relentlessly toward the very center of the galaxy. This process solves a fundamental problem for galaxy evolution: how to get fresh fuel from the outskirts, where it's plentiful, into the crowded central regions, where it's needed to form new stars or feed the waiting supermassive black hole. Without this mechanism, that gas might simply continue orbiting quietly in the outer disk, never contributing to the activity at the galaxy's heart. The bar acts as a direct pipeline, ensuring a steady and dramatic inflow of raw material. The consequences of this cosmic freight train are profound and twofold. First, this influx of gas into the central regions, often called a nuclear starburst, can trigger an explosive wave of new star formation. The gas piles up, becomes compressed, and collapses under its own gravity, igniting into millions of new stars and creating a brilliantly luminous central star cluster. This is how some galaxies develop what's known as a nuclear ring, a dazzling circle of intense stellar activity directly fueled by the bar's pipeline. Second, some of this gas doesn't form stars. Instead, it continues its journey all the way down to the very center, where it's destined to fall onto the waiting supermassive black hole. This delivery of fuel can switch the black hole from a quiescent state into an active phase, powering it up as a brilliant quasar or active galactic nucleus. The energy outburst from this activated black hole can then blow away remaining gas, effectively shutting down further star formation and regulating the galaxy's growth. In this way, the galactic bar is a master regulator, directly linking the large-scale structure of the galaxy to the frenetic activity in its core. It demonstrates that a galaxy is a deeply interconnected system, where a change in one area, like the formation of a bar, can set off a chain of events that reshapes its entire future, dictating whether its center will blaze with the light of newborn stars or the intense radiation of an awakened giant. And just as the immense gravity of a galaxy cluster can hold hundreds of galaxies captive, that same gravity can perform an even more incredible feat. It can bend the very fabric of space-time itself, creating one of nature's most powerful telescopes. This phenomenon is known as gravitational lensing, a spectacular validation of Einstein's theory of general relativity that transforms the universe's most massive structures into cosmic magnifying glasses. The principle is as profound as it is elegant. Einstein revealed that gravity isn't just a force between masses, it's a curvature of space-time. A massive object like a galaxy cluster creates a deep dimple in this cosmic fabric. Now imagine light from a distant object traveling across the universe in a straight line. If its path takes it near this massive dimple, the light will follow the curve of the distorted space, just as a marble would roll around the rim of a bowl. This bending of light by gravity is gravitational lensing. When the alignment between a distant background object, a massive foreground cluster, and our telescope is just right, the effects are nothing short of miraculous. Instead of seeing a single, faint smudge of a galaxy billions of light years away, we see multiple, distorted, and magnificently stretched images of it. The cluster's gravity can smear the distant galaxy's light into bright arcs and rings that curve around the cluster's center, like looking at a street lamp through the bottom of a wine glass. In some cases, we can even see the same distant galaxy replicated 4 or 5 times in a single image, a celestial echo created by the different paths its light has taken around the gravitational well. These cosmic mirages are more than just beautiful curiosities. They are one of astronomy's most powerful tools. This natural telescope effect allows us to do 2 extraordinary things. First, it magnifies the light from incredibly faint, distant objects, bringing into view the earliest galaxies that formed after the Big Bang, galaxies so remote that their light is otherwise too faint for even our most powerful human-built telescopes to detect. It's as if the universe itself is providing us with a giant lens to peer back into its own infancy. Second, the specific way the light is distorted allows astronomers to map the distribution of mass within the foreground cluster itself. This includes not just the visible galaxies, but crucially, the vast halos of dark matter that make up most of the cluster's weight. By analyzing the intricate patterns of lensed light, scientists can literally trace the outline of the invisible, creating detailed maps of where the dark matter lies and confirming its role as the primary scaffolding of the cosmos. Iconic images from the Hubble and James Webb Space Telescopes, like those of the galaxy cluster Abell 1689, showcase this phenomenon in breathtaking detail. The photo is a beautiful chaos. A collection of giant yellow elliptical galaxies at the cluster's heart is surrounded by a stunning array of blue streaks and arcs, each one a single, vastly magnified background galaxy stretched across the sky. These images are not artistic renditions. They are direct observational proof of Einstein's genius and a powerful reminder that the universe is not only stranger than we imagine, but often more generous, providing its own natural observatories to help us uncover its deepest secrets. Just as planets have a habitable zone where conditions are just right for liquid water, galaxies themselves may possess a broader sweet spot for life, a galactic habitable zone. This fascinating concept suggests that the chances for complex life to emerge are not uniformly distributed across a galaxy. Some neighborhoods are simply more dangerous or impoverished than others. If you think of a galaxy as a vast metropolis, then the downtown core is a chaotic, high-energy district, while the distant suburbs might be lacking in essential resources. Our solar system's position, about halfway out from the center of the Milky Way, appears to be located in one of these more favorable galactic suburbs. The dangers of the inner galaxy are numerous and extreme. The galactic center is an environment of immense violence, dominated by the ferocious gravitational pull and radiation from the supermassive black hole, Sagittarius, a star. When active, this beast can unleash devastating blasts of X-rays and gamma rays that would sterilize any planetary system in its vicinity. Furthermore, the density of stars in the central bulge is exponentially higher than in our quiet spiral arm. With stars packed so closely together, the chances of a nearby supernova explosion, a cataclysmic event that would bathe nearby worlds in lethal radiation, become terrifyingly high. A planet orbiting a star in this crowded core would face a constant existential threat, its atmosphere potentially being stripped away and its surface scoured clean by these repeated cosmic outbursts, making the stable, billion-year-long quietude needed for life to evolve nearly impossible. Conversely, the outer reaches of the galactic disk present a different but equally limiting set of challenges. The primary issue here is a poverty of elements. The raw materials for rocky planets like Earth and for the chemistry of life itself, elements such as carbon, nitrogen, oxygen, and iron, are forged in the hearts of massive stars and dispersed through supernova explosions. This process of cosmic enrichment happens most vigorously in the inner galaxy, where star formation has been ongoing and intense for billions of years. Out in the sparse galactic hinterlands, there have been far fewer stellar generations to manufacture and spread these heavy elements. A planetary system forming in this region would likely be built from a much more primordial soup of gas, predominantly hydrogen and helium, making it difficult to even form solid terrestrial planets. Without a rocky world with a protective metal core and a stable atmosphere, the prospects for life as we know it are incredibly slim. This paints a compelling picture of a galactic Goldilocks zone, a ring within the spiral arms where conditions are just right. It's a region far enough from the violent center to avoid frequent sterilizing radiation events, yet close enough in to have been enriched with a sufficient abundance of those crucial heavy elements from generations of past stars. This zone would also benefit from the relative stability of a well-ordered galactic disk, avoiding the gravitational chaos of the inner halo. Our own position in the Milky Way seems to fit this description perfectly, placing us in a quiet, resource-rich neighborhood that has allowed our planet to thrive for billions of years. It suggests that when we search for other intelligent civilizations, we might want to focus our efforts not just on Earth-like planets, but on stars orbiting within this galactic sweet spot, the most promising real estate the cosmos has to offer. To truly unravel the complex tapestry of galaxy formation, cosmologists couldn't rely on observation alone. They had to learn how to build their own universes inside a machine. This is the realm of computational cosmology, where some of the most powerful supercomputers on Earth are tasked with running the most ambitious physics experiments ever conceived. These aren't simple animations, they are sophisticated virtual universes governed by the precise laws of physics, where billions of particles of dark matter and gas are set in motion to see what structures emerge over billions of years of simulated time. The sheer scale of the calculations is almost beyond comprehension. A single, high-resolution simulation can track the interactions of over 1 trillion particles, each representing a parcel of dark matter or a cloud of gas, all influencing each other through gravity and hydrodynamics. Evolving this virtual cosmos from the smooth, early universe to the present day requires millions of CPU hours, often running on thousands of processors working in tandem for months on end. It's a monumental expenditure of processing power, all dedicated to answering one of science's grandest questions. How did we get here? The magic of these simulations lies in their recipe, which must include every known ingredient that shapes a galaxy's life. The foundation is always the gravitational pull of dark matter, which forms the invisible cosmic scaffolding. Then comes the ordinary baryonic matter, the gas that will eventually form stars. But the gas doesn't just passively fall into the dark matter halos. It behaves according to the complex rules of fluid dynamics, experiencing pressure, heating, and cooling. As pockets of gas collapse to form stars, the simulation must account for the energy and heavy elements those stars inject back into their surroundings through stellar winds and supernova explosions. Perhaps most crucially, the model must include the powerful feedback from supermassive black holes, whose energetic outbursts can heat and expel gas on a galactic scale. Leaving out any one of these processes results in a virtual universe that looks nothing like our own. Without supernova feedback, for instance, galaxies form far too many stars too quickly, ending up much smaller and brighter than real galaxies. Without black hole feedback, the simulations fail to produce the massive, red and dead elliptical galaxies we observe. It is only by carefully tuning this intricate dance of creation and destruction that the simulations begin to yield galaxies with the correct sizes, shapes, and colors. The ultimate goal isn't to create a perfect digital replica of a specific galaxy, but to produce a vast synthetic universe filled with a realistic population of galaxies that statistically match what our telescopes see. When scientists run these simulations, they can analyze the properties of millions of virtual galaxies, their masses, their rotation speeds, their morphologies, and compare these distributions to massive real-world surveys like the Sloan Digital Sky Survey. The remarkable agreement between the virtual and the real is a powerful validation of our entire cosmological model, the lambda cold dark matter paradigm. It tells us that our understanding of the underlying physics, from gravity to the behavior of dark matter, is fundamentally correct. These digital universes have become indispensable laboratories, allowing us to watch a galactic collision unfold from any angle. Rewind a billion years of evolution to see how a galaxy assembled, or conduct experiments that are impossible in the real world, like turning off dark matter to see how a galaxy flies apart. They are the ultimate tools for testing our theories, offering a dynamic, evolving view of the cosmos that complements the single, frozen snapshot we get from our telescopes, and they continue to refine our story of how chaos gave rise to order and how simple particles gave rise to the breathtaking beauty of the cosmic web. But sometimes the grand collisions that create elliptical giants also give rise to something entirely new and unexpected. During the slow, gravitational dance of two merging spiral galaxies, their immense tidal forces don't just warp their shapes, they can violently fling billions of stars and enormous reservoirs of gas out into intergalactic space. This ejected material forms spectacular, luminous arcs stretching hundreds of thousands of light years, known as tidal tails. For a long time, astronomers viewed these structures as beautiful but tragic cosmic debris, destined to slowly fade away as they drift into the emptiness between galaxies. However, observations have revealed a far more fascinating fate for some of this material. In the densest regions of these tidal tails, something miraculous can happen. The ejected gas and stars can collapse under their own gravity and ignite with new star formation, giving birth to entirely new, small galaxies right there in the wreckage of the old. These are not primordial galaxies, they are entirely new classes of objects called tidal dwarf galaxies. What makes these tiny galaxies so extraordinary and so different from all the others we've discussed is what they are made of, or more accurately, what they are missing. Remember that every galaxy we know, from the faintest dwarf to the largest cluster, is believed to be dominated and defined by its massive halo of dark matter. This invisible scaffolding is the gravitational anchor that pulled everything together in the first place. But a tidal dwarf galaxy forms from the visible material, the gas and stars, that was ripped out of the disks of its parent galaxies. This is a critical distinction. The dark matter halos of the original galaxies are so vast and diffuse that they simply don't get pulled out into the tidal tails. They remain as the unseen foundation of the merger remnant. The material that forms the tidal dwarf is therefore almost purely baryonic, made of the ordinary matter we can see and touch. This creates a unique and testable prediction. If these objects are truly devoid of dark matter, they should rotate in a very specific way. The rotation speed of their stars and gas should be governed solely by the gravitational pull of the visible mass within them. This is in stark contrast to a normal galaxy, where the rotation curve remains flat due to the overwhelming influence of the unseen dark matter halo. Incredibly, when astronomers measure the rotation of tidal dwarf galaxies, that's exactly what they find. Their outer gas clouds rotate more slowly, following the expected Keplerian decline, just as planets do around a star. This provides compelling, direct evidence that these systems are indeed lacking their own dark matter, making them unique cosmic orphans. They are not rooted in the ancient gravitational wells of dark matter like all other galaxies. They are fleeting, second-generation structures, born from the chaos of a collision and shining solely by the light of their own stars. Their very existence is a powerful footnote in the story of galactic evolution, demonstrating that while dark matter is essential for building the first galaxies, the universe can occasionally craft new island universes through pure, violent mechanics, leaving them to sail through the cosmos without their dark, invisible anchors. We've explored the immense gravitational forces that sculpt galaxies and the violent feedback that regulates their growth. But there's another, more subtle force weaving through the cosmic tapestry, one that is invisible to our eyes yet profoundly shapes the life of a galaxy. This force is magnetism. Unlike the gravity of dark matter, which pulls from vast distances, or the explosive feedback from black holes, galactic magnetic fields are a pervasive, whisper-thin presence, an invisible web stretching between the stars. They are incredibly weak, far weaker than a common fridge magnet, yet they are everywhere, threading through the entire expanse of a galactic disk and reaching far out into its halo. Their origin is one of the great unsolved puzzles in astrophysics, a mystery that begins in the chaotic aftermath of the Big Bang. The prevailing theory for how these fields grew to such colossal scales is a process known as the galactic dynamo. Imagine a simple loop of wire and a moving magnet. This setup can generate an electric current, a principle used in power plants worldwide. The galactic dynamo applies this same idea on a million light-year scale, but instead of wire, the conductor is the galaxy's own electrically conductive plasma, the ionized gas that fills the space between stars. The moving magnet is provided by the galaxy's differential rotation. The inner parts of the disk rotate faster than the outer parts, and this shearing motion can stretch and twist any weak, pre-existing magnetic field lines. Turbulence from supernova explosions and stellar winds further stirs this magnetic soup, winding the field lines into a stronger, more organized structure. Over hundreds of millions of years, this self-amplifying process can take a faint, primordial magnetic seed and build it into the large-scale field we detect today. But where did that initial seed field come from? That remains an open question, with possibilities ranging from processes in the very early universe to fields generated by the first stars and galaxies themselves. Once established, these magnetic fields become a fundamental part of the galactic ecosystem, influencing nearly every process within it. Their most visible role is in star formation. Giant molecular clouds, the birthplaces of stars, are supported against their own gravity by internal pressure and turbulence. Magnetic fields provide an additional support force, acting like a cosmic scaffolding that helps prevent the cloud from collapsing too quickly. They can channel flows of gas, guiding material into the densest regions and ultimately helping to determine the final mass of a newborn star. Without magnetic fields, star formation might be a far more violent and inefficient process. Furthermore, these fields leave their imprint on the very dust of the galaxy. The tiny, elongated dust grains tend to align themselves with the direction of the magnetic field lines, and because of this, they polarize the light that passes through them. By measuring this polarization, astronomers can literally map the magnetic field structure of our own Milky Way and other galaxies, revealing beautiful patterns that flow along the spiral arms and erupt from regions of intense stellar activity. Perhaps their most dramatic role, however, is in governing the journey of cosmic rays. These are not rays of light, but incredibly high-energy subatomic particles, mostly protons, racing through space at nearly the speed of light. They are accelerated by shock waves from supernova explosions, and if they traveled in straight lines, they would zip across a galaxy and escape into intergalactic space in just a few hundred years. But they don't travel straight. The galaxy's magnetic field acts as a vast, tangled maze. A cosmic ray proton, being electrically charged, is forced to spiral around the magnetic field lines, changing direction constantly as it bounces from one region to another. This process confines these particles to the galaxy for millions of years, turning them into a persistent, high-energy component of the interstellar medium. The magnetic fields effectively act as a containment vessel for this radiation, which plays a crucial role in ionizing gas clouds and influencing the chemistry of the space between the stars. So, while we cannot see them directly, galactic magnetic fields are the silent conductors of a grand cosmic orchestra, directing the flow of gas, shaping the birth of stars, and trapping the most energetic particles in the universe within their invisible magnetic embrace. But to truly map this vast cosmic architecture, to measure the distances between these grand structures and understand the universe's expansion, astronomers needed a reliable ruler, a way to gauge how far away a galaxy truly is. The key to unlocking this cosmic distance scale was discovered not in the intricate details of a galaxy's shape or brightness, but in the very color of its light. This profound discovery hinges on a phenomenon known as redshift, and it provides us with a direct window into the dynamic, expanding fabric of the cosmos. The principle behind it is surprisingly accessible, rooted in a familiar everyday experience, the Doppler effect. Just as the pitch of a siren drops from a high wail to a low groan as an ambulance races past you, the light from a moving object is similarly shifted. If a galaxy is moving toward us, the waves of its light are compressed, making them appear bluer. If it's moving away, the light waves are stretched, making them appear redder. In the 1920s, astronomer Edwin Hubble, working with the most powerful telescope of his era, made a staggering observation. He found that the light from nearly every galaxy he observed was shifted toward the red end of the spectrum. And it wasn't just a little bit red. The farther away a galaxy was, the greater its redshift. This was the revolutionary clue. The universe wasn't static, it was expanding, with every galaxy rushing away from every other galaxy as the very space between them stretches. The redshift of a galaxy isn't primarily caused by its motion through space, like the ambulance. It's caused by the expansion of space itself. As a beam of light travels for millions or billions of years to reach us, the space it's traveling through stretches, and this stretching elongates the light waves, systematically shifting them toward redder wavelength. The greater the distance the light has traveled, the more space has expanded during its journey, and the larger the redshift we measure. This relationship between redshift and distance is so consistent and reliable that astronomers use it as the ultimate cosmic odosimeter. By simply taking a spectrum of a galaxy and measuring how much its known signature light waves have been stretched, they can immediately calculate its distance. This single tool allows us to construct three-dimensional maps of the universe, plotting the positions of millions of galaxies and revealing the immense cosmic web of filaments and voids. This expanding universe was the first great pillar of evidence for the Big Bang theory, pointing back to a moment when everything was compressed into an infinitely hot, dense point. But the story of redshift held an even bigger surprise. In the late 1990s, two independent teams of astronomers were using redshift to measure the distances to extremely far-off supernovae, expecting to see the rate of the universe's expansion slowing down over time due to the pull of gravity. To their utter astonishment, they found the opposite. The most distant galaxies, whose light has been traveling to us for billions of years, were receding slower than expected. The closer, more recent galaxies were flying away faster. The expansion of the universe wasn't slowing down, it was speeding up. This was like tossing a ball into the air and watching it not only fail to fall back down, but instead shoot away from you at an ever-increasing velocity. This breathtaking discovery could only mean one thing. Some mysterious, repulsive force must be counteracting gravity on the largest scales, a force that was dubbed dark energy. Redshift, the simple stretching of light, had not only revealed the universe's expansion, but had also uncovered its greatest mystery. It showed us that the cosmos is dominated by an unseen energy that is tearing space itself apart at an accelerating rate, dictating a future where galaxies beyond our local group will eventually recede over a cosmological horizon. their light stretched beyond detectability, leaving any future astronomers in a lonely island universe. This humble color shift in starlight is our most powerful tool for reading the history and destiny of the cosmos, a fundamental echo of the universe's dynamic nature written in every photon that reaches our telescopes. While the supermassive black hole at the center of our Milky Way is currently a quiet, sleeping giant, this is not its permanent state. In fact, this serene phase is just one possible mode in a dramatic cycle of activity. And when these cosmic engines awaken, they transform into the most powerful and persistent sources of energy in the entire universe. This activated state is what astronomers call an active galactic nucleus, or AN, and it represents a black hole's transition from a passive anchor to a dominant, brilliant powerhouse. The trigger for this astonishing transformation is a simple matter of supply and demand. A supermassive black hole is by its very nature a ravenous consumer. For it to remain quiet, it must be starved of fuel. But if a sudden and massive influx of material occurs, perhaps a vast cloud of interstellar gas is driven inward by a galactic bar, or a smaller galaxy is consumed in a collision, funneling its gas toward the center, the black hole's environment changes completely. This gas doesn't fall in directly. Instead, it forms a swirling, frantic whirlpool of matter known as an accretion disk. As this material spirals inward at nearly the speed of light, particles smash together, generating incredible friction and heat. The temperatures in this disk can soar to millions of degrees, causing it to glow with an intense, blinding light that can outshine every single star in the entire host galaxy combined. This is the heart of an active nucleus, a tiny region smaller than our solar system that produces more energy than 100 billion suns. The sheer luminosity is only part of the story. The way this energy is released is what truly defines an AGN's impact. In some cases, the incredible magnetic fields generated by the churning accretion disk can focus and accelerate some of the infalling material into two narrow, oppositely directed jets that shoot out from the poles of the black hole at nearly the speed of light. These jets, composed of energetic particles and magnetic fields, can stretch for hundreds of thousands, even millions of light years, far beyond the boundaries of the host galaxy itself. When one of these relativistic jets is pointed directly at Earth, we see an especially bright type of AGN known as a blazar, its intense beam of radiation making it visible across the cosmos. But even when not aimed at us, the energy released is staggering. These jets pump enormous amounts of energy into the surrounding intergalactic medium within a galaxy cluster, heating the thin plasma that floats between galaxies and preventing it from cooling and falling in to form new stars. This is AGN feedback on a truly colossal scale, where a single object at the center of one galaxy can dictate the star-forming future of hundreds of its neighbors, effectively putting the brakes on the growth of an entire galactic city. Beyond the jets, the central engine can also drive powerful winds of hot gas that blow outward in all directions. These aren't the gentle winds of a terrestrial breeze, they are hurricanes of million-degree plasma, rushing away from the galaxy's center at thousands of kilometers per second. This outflow violently interacts with the galaxy's remaining reservoirs of cold gas, the very raw material for new stars. It heats the gas, pushes it around, and in extreme cases, can blow it completely out of the galaxy and into the void. This process, known as quenching, is how an active galactic nucleus can effectively starve its own host galaxy, shutting down star formation and steering its evolution toward a red and dead future. The active phase is ultimately self-limiting. By expelling or consuming the available fuel, the black hole eventually starves itself back into a period of quiescence. This creates a cycle of feeding and feedback, a cosmic balancing act that links the growth of the black hole to the growth of the galaxy itself, ensuring that neither becomes too large too quickly and explaining the mysterious correlation between the mass of a galaxy's central bulge and the mass of its hidden dark heart. We've seen how galaxies form and evolve through collisions and feedback, but the sheer diversity in their final forms is perhaps just as breathtaking as their origins. When we picture a galaxy, many of us imagine something like our own Milky Way or Andromeda, a majestic spiral spanning 100,000 light-years. But this image represents only one point on a truly staggering spectrum of size. The range of galactic scales is so vast it challenges our everyday understanding of what an island universe can be. At one extreme lie the universe's most humble galactic constituents, ultra-compact dwarf galaxies. These are the galactic minnows, often just 200 or 300 light-years across. To put that into perspective, that's only about twice the distance from our Sun to the farthest reaches of the Oort cloud, the icy shell of comets at the edge of our own solar system. These tiny galaxies pack tens of millions of stars into that incredibly small volume, making them far denser than any giant elliptical or spiral. In fact, if you were standing on a planet in the center of one, your night sky would be a continuous, brilliant tapestry of stars, with the closest ones separated by mere light weeks instead of light years. They are thought to be the leftover cores of larger dwarf galaxies that had their outer stars violently stripped away during close encounters with galactic giants, leaving behind only their dense, star-packed hearts. On the opposite end of the scale reside the true titans of the galactic world, the giant elliptical galaxies. These are the cosmic cities, the end results of multiple galactic mergers, and they can be absolutely colossal. Galaxies like Messier 87, which anchors the Virgo cluster, can span well over 500,000 light-years from edge to edge. Their diffuse, shimmering halos of ancient stars extend so far that they gently bleed into the halos of their neighboring galaxies, creating a continuous web of starlight throughout the entire cluster. These galaxies represent the ultimate expression of galactic growth through cannibalism, having consumed countless smaller neighbors over billions of years to achieve their immense girth. Yet even these giants were recently dethroned by a discovery so immense it redefines our very notion of a single structure. Meet Alcyoneus, a galaxy located about 3 billion light-years away. When astronomers mapped its radio emissions, twin lobes of plasma ejected by its active supermassive black hole, they found something that defied belief. These lobes stretch across an incomprehensible 16 million light-years of space. That is 160 times the diameter of our entire Milky Way. To grasp that scale, if you could shrink our galaxy down to the size of a single grain of sand, Alcyoneus would be the length of a full-sized school bus. This colossal structure isn't made of stars. It's a testament to the raw, unleashed power of its central engine, a supermassive black hole that must have had a catastrophic feeding event in the distant past, ejecting jets of material on a scale never before imagined. Alcyoneus isn't just a galaxy. It is the largest single structure of galactic origin ever identified, a cosmic leviathan whose true size reveals that even our most expansive ideas about the universe can still be dwarfed by reality. Just as a city's environment shapes its character with quiet suburbs fostering a different lifestyle than a bustling downtown, a galaxy's fate is profoundly sculpted by its cosmic address. This is one of the most critical factors in galactic evolution: location, location, location. A galaxy does not evolve in isolation. Its entire life story is written by its place within the immense cosmic web. Whether it lives a solitary existence as a field galaxy in a quiet cosmic neighborhood or is crammed into a dense, violent galaxy cluster determines its access to resources, its frequency of interactions, and ultimately, its longevity as a star-forming entity. For a field galaxy floating alone in a vast cosmic void, life is generally serene. These isolated islands have a steady, if slow, supply of intergalactic gas to draw from, a private reservoir that allows them to form new stars at their own leisurely pace for billions of years. They experience few, if any, disruptive collisions, allowing them to maintain their beautiful spiral structures. Theirs is a story of gentle, internal evolution, governed by their own internal dynamics like the formation of a bar or the steady churn of the galactic fountain. They are the cosmic equivalents of quiet, rural towns, growing slowly and maintaining their character over eons. In stark contrast, a galaxy that falls into a massive cluster enters a chaotic and dangerous metropolis. Galaxy clusters are the most massive gravitationally bound structures in the universe, containing hundreds or even thousands of galaxies swarming in a relatively small volume of space, all immersed in a superheated, thin plasma known as the intracluster medium. This environment is so extreme that it actively attacks and dismantles a galaxy's ability to form new stars through several ruthless processes. The first and perhaps most dramatic is ram pressure stripping. Imagine a galaxy falling into a cluster is like a car driving through a heavy downpour. The intracluster medium acts as a powerful headwind. For a galaxy, this wind is a storm of million-degree particles. As the galaxy moves at incredible speeds through this superheated fog, the pressure exerted by this medium can literally strip the cold gas right out of the galactic disk. This gas, the very lifeblood for future stars, is ripped away, leaving behind a trailing wake of lost material like cosmic exhaust. The galaxy is left gas-poor and unable to form new stars, its spiral structure beginning to fade as its primary fuel supply is stolen. If ram pressure is a sudden, violent assault, then strangulation is a slower, more insidious fate. Also known as starvation, this process cuts off a galaxy's supply of fresh fuel. When a galaxy is captured by a cluster's immense gravity, the vast reservoirs of cooler intergalactic gas that it once used to replenish its disk are cut off. The galaxy is now isolated from the cosmic gas grid, forced to rely solely on whatever fuel it has left in its internal tanks. It continues to form stars, but it's now living on a finite budget. It slowly consumes its remaining gas, and as that supply dwindles, its star formation rate dwindles with it. The galaxy isn't killed quickly. It's slowly starved of the resources it needs to sustain itself, leading to a gradual fading and a transition from blue to red as its last massive blue stars die out. Adding to this environmental pressure is a process called galaxy harassment. In the crowded downtown core of a cluster, high-speed, fly-by encounters with other galaxies are constant. These are not the slow, merging collisions that create new ellipticals, but rapid, glancing blows. Each close pass gravitationally jolts the galaxy, disturbing its structure, puffing up its disk, and potentially triggering bursts of star formation that rapidly deplete its remaining gas. Over time, this relentless harassment can morph a once orderly spiral into a bloated, irregular, or even spheroidal shape, stripping away its identity through a death by 1,000 gravitational cuts. The combined effect of these environmental processes is a dramatic difference in galactic demographics. Dense clusters are dominated by red and dead elliptical and lenticular galaxies, smooth, gas-poor systems where star formation ceased long ago. The quiet field, however, remains the haven for majestic, blue spiral galaxies where the cycle of star birth and death continues. A galaxy's destiny, it turns out, is not written solely in its stars but in the crowdedness of its cosmic neighborhood. While the sheer scale of a galactic collision suggests a scene of unimaginable destruction, the reality of what happens when these titans meet is far more nuanced and strangely beautiful. It's a common misconception to picture a cataclysm of stars smashing into each other like cars in a cosmic freeway pile up. But the truth is, in a galaxy merger, the stars themselves almost never collide. The distances between them are so astronomically vast that they simply pass through the opposing galaxy like two clouds of smoke merging, their individual paths barely disturbed. The real drama, the force that utterly reshapes these galaxies, is not contact but gravity. It is the invisible hand of gravity that orchestrates the entire event, weaving chaos into new and spectacular forms. The gravitational tides unleashed during a close encounter are so powerful that they can sculpt galaxies into temporary, breathtaking shapes that seem more like celestial works of art than natural phenomena. One of the most stunning examples is the formation of a ring galaxy. This occurs when a smaller galaxy plunges directly through the center of a larger spiral disk, like a bullet through a bullseye. The precise gravitational shockwave from this pass-through propagates outward through the larger galaxy's disk. It doesn't push the existing stars. Instead, it compresses the gas and dust in a wave that triggers a furious burst of star formation in a perfect, expanding circle. The result is a galaxy that looks like a diamond ring set against the velvet of space, with a bright central hub and a brilliant blue circle of newborn stars swirling around it. The Cartwheel Galaxy is a famous and pristine example of this rare and beautiful structure, a frozen moment in a billion-year-long interaction. In other mergers, particularly those involving elliptical galaxies or the final stages of a major collision, we can observe another ghostly signature of gravitational tides, shell structures. These appear as faint, concentric arcs of stars layered around the merged galaxy, much like the ripples from a stone dropped in a pond. These shells are not waves of star formation, but rather the trapped orbits of stars that were ripped from their original galaxies. As the galaxies merge, stars are slung out on long, looping trajectories. They travel outwards, slow down at the apex of their orbit, and then fall back in, creating these delicate caustic patterns in space. Observing a galaxy with multiple nested shells is like reading its history. Each shell marks a major orbital period, telling us about the timing and violence of the past merger that created them. But the most profound and lasting transformation occurs through a process known as violent relaxation. This is the mechanism that erases the beautiful spiral structures forever and forges the giant elliptical galaxies that dominate galaxy clusters. While the stars may not physically collide, their gravitational orbits are thrown into utter chaos. The smooth, orderly gravitational field that once guided each star in a neat circular path around the galaxy's center is suddenly and violently disrupted by the intruding galaxy. The stars are yanked and pulled in every direction, their orbits becoming randomized. It's the difference between a calm, organized marathon and a mosh pit. The energy of the system is redistributed from ordered rotation into random, disordered motion. As the two galaxies finally coalesce into one, this new, chaotic system seeks a new equilibrium. The stars settle into a new, balanced configuration, but it is one governed by statistics, not by orderly rotation. They end up orbiting the new common center of gravity in every possible direction, creating a featureless, three-dimensional swarm, the hallmark of an elliptical galaxy. Any remaining gas is either consumed in a final, ferocious burst of star formation or blown away by the resulting supernova winds, leaving behind a red and dead population of old stars. This is the ultimate fate of a major merger, the destruction of two beautiful, ordered spirals and the birth of a single, giant and smooth elliptical, a cosmic phoenix born from gravitational chaos. But while these galactic collisions provide the grand, sweeping narrative of a galaxy's growth, the finer details of that history are often written in the faintest of ink, visible only to our most powerful telescopes. Look closely at the halo of our Milky Way, far from the bright plane of the galactic disk, and you will find more than just randomly scattered ancient stars. You'll discover the ghostly remnants of past meals, the fossilized evidence of our galaxy's cannibalistic history, written in delicate, swirling rivers of stars known as stellar streams. These are not man-made structures. They are the shimmering, dissolving trails of dwarf galaxies and globular clusters that ventured too close to the Milky Way's immense gravitational pull and were torn apart by tidal forces over billions of years. Imagine a small satellite galaxy, perhaps 1/10 the size of our own, on a long, looping orbit around the Milky Way. Each time it makes a close pass, our galaxy's gravity exerts a stronger pull on the side of the dwarf that is closer than on the side that is farther away. This difference in gravitational force, known as a tidal force, acts like a cosmic string of taffy, stretching the smaller galaxy until it can no longer hold itself together. Stars are ripped from its grasp, but they don't just vanish. They are flung out into space, yet they continue to orbit the Milky Way on paths very similar to their original parent galaxy. Over many orbits, these escaped stars become strewn out along the original orbital path, forming a long, incredibly faint ribbon that completely encircles our galaxy. What was once a distinct spherical dwarf galaxy is now a cosmic signature, a stellar stream that can stretch for hundreds of thousands of light years, a single orbit preserving the memory of a structure that no longer exists. These streams are far more than just beautiful relics. They are powerful tools for a field known as galactic archaeology. By mapping the positions, motions, and chemical compositions of the stars within a stream, astronomers can rewind the cosmic clock. Each stream tells a story. For instance, the Sagittarius stream, the most prominent one in our sky, is the dissolving remains of the Sagittarius dwarf spheroidal galaxy, which we are currently in the process of consuming. The very fact that this stream is still coherent tells us that the accretion event is relatively recent on a galactic timescale. Furthermore, the stars in this stream are ancient and metal-poor, confirming that the original dwarf galaxy was a primitive building block from the early universe. Other streams, like the one associated with the globular cluster Palomar 5, show us how even the densest star clusters can be unraveled by the galactic tide, slowly donating their stars to the halo. Perhaps their most profound application, however, lies in mapping the invisible. The precise shape and density of a stellar stream is exquisitely sensitive to the gravitational field it moves through. As a stream orbits the galaxy, any clumpiness or substructure in the dark matter halo will subtly distort it. Much like a garden hose lying on the ground will show a bump if there's a rock underneath it. By studying the finest details of a stream's structure, astronomers can therefore trace out the distribution of dark matter in the Milky Way's halo with incredible precision, revealing not just the smooth overall distribution, but potentially even the presence of smaller, invisible dark matter subhalos that have never been seen directly. These faint rivers of stars, the final tiers of ancient galaxies, have become one of our most precise instruments for uncovering the hidden architecture of our cosmic home. To truly comprehend the scale of galactic evolution, we must first abandon our human-centered perception of time. The majestic spiral of the Milky Way above us was not built in a year, a millennium, or even a million years. Its construction is a project of almost unimaginable duration, a saga written in billions of years, where the most dramatic chapters unfold over timescales that dwarf the entire history of life on our planet. If we were to compress the entire 13.8 billion-year history of the universe into a single calendar year, with the Big Bang at the first moment of January 1st, our entire recorded human history would occupy less than the final second of December 31st. On this scale, the assembly of our galaxy is a story that spans months. The very first seeds of the Milky Way, those primordial clumps of dark matter and gas, began coalescing when the universe was only a few 100 million years old, sometime in late January or early February on our cosmic calendar. The process of building its central bulge and the initial protodisk was a long and violent one, dominated by a series of major mergers. The most significant of these events happened around 10 billion years ago, when a large dwarf galaxy astronomers call Gaia Enceladus was utterly consumed by our young galaxy. This colossal collision, which would have lit up the early cosmos, fundamentally reshaped the Milky Way, puffing up its disk and scattering a vast population of stars into what would become our galactic halo. This single merger event alone took hundreds of millions of years to fully play out, from the first close encounter to the final assimilation. But the construction didn't stop there. After this main phase of building, the galaxy entered a longer, more serene period of growth known as inside-out formation. Imagine a city building its downtown core first and then slowly expanding its suburbs outward over centuries. The Milky Way did the same. The inner regions of the galactic disk assembled and settled first with the outer disk where our solar system resides, forming much later from gas that slowly accreted over billions of years. This is why stars in the inner galaxy are generally older and more metal-rich, while those farther out, like our Sun, are younger and formed from gas that was less enriched by previous generations of stars. This gradual, steady growth is a form of secular evolution, the internal evolution that continuously refines a galaxy's structure through processes like the churning of spiral arms and the action of the central bar, slowly funneling gas inward over eons. And the work is still not finished. The Milky Way continues to evolve today, right now, as you look up at the night sky. It is a dynamic, living structure. We are, as we discussed, currently in the process of digesting the Sagittarius dwarf spheroidal galaxy, stretching it into a shimmering stream of stars that wraps around us. We are also actively accreting fresh, pristine gas from the circumgalactic medium, the vast reservoir of material that surrounds our galaxy. This cold flow of gas provides new fuel for future star formation, ensuring the cycle of birth and death continues. Furthermore, we are on an inevitable collision course with the Andromeda Galaxy, a merger that will begin in earnest in about 4.5 billion years and will take over 1 billion years to complete, ultimately transforming both spirals into a new, giant elliptical galaxy. This grand timeline puts our own existence into a humbling perspective. Every star we see, every constellation we recognize, is a fleeting snapshot in a multi-billion-year movie. Our entire solar system, from the Sun's birth to its eventual death, is just a single scene in this epic. We are living in a brief moment of relative galactic peace, a peaceful interlude between the violent mergers of the past and the colossal collision of the future, granted a front-row seat to a show whose full performance lasts for cosmic eternity. But the ferocity of these galactic winds is not always confined to reshaping their home galaxy alone. In the most extreme cosmic environments, where star formation reaches a fever pitch or a supermassive black hole feasts with unmatched gluttony, these outflows can achieve truly escape velocity, breaking free from the galaxy's gravitational grasp entirely and venting its enriched contents into the vast, empty reaches of intergalactic space. This is the ultimate expression of galactic feedback, a process so powerful it can permanently alter a galaxy's fate and seed the entire cosmos with the building blocks for future worlds. The stage for this drama is often set in a starburst galaxy, a system gripped by a ferocious and unsustainable binge of star formation. Imagine a celestial metropolis where stars are being born not in quiet suburbs, but in a frantic, wall-to-wall construction boom, with stellar nurseries packed so tightly that the collective radiation and stellar winds from massive young stars create an environment of unimaginable pressure. It's a pressure cooker with no release valve, and eventually the lid must blow. The primary explosive force comes from supernova. When these massive stars die, they don't go quietly. They detonate in rapid succession, their collective shockwaves merging into a single, colossal bubble of superheated gas that erupts outward. This isn't a gentle fountain recirculating material. It's a volcanic explosion. The energy is so immense that it can punch straight through the galaxy's disk, propelling a biconical hurricane of million-degree plasma out above and below the galactic plane at speeds exceeding 2 million miles per hour. We can observe these spectacular structures in other galaxies as vast, glowing lobes of X-ray and radio emission, stretching tens of thousands of light years into the void. These are not subtle features, they are titanic signatures of a galaxy violently expelling its own lifeblood. The consequences of this great escape are nothing short of cosmic. The most immediate and dramatic effect is on the galaxy itself. This ejected gas is the primary reservoir of fuel for future generations of stars. By violently purging it, the galactic wind effectively starves the galaxy, cutting off the supply of raw material needed for continued star birth. This is a powerful self-regulating mechanism. The very process that creates a brilliant blue starburst galaxy also contains the seeds of its own demise, often leading to a future where the galaxy is left a quiescent, red and dead system, its stellar population slowly aging with no new stars to renew its light. But the story doesn't end at the galactic border. The material blown out in these winds doesn't just disappear. It is injected into the circumgalactic and intergalactic medium, the thin plasma that fills the spaces between galaxies. This ejected material is crucially important because it is heavily enriched with heavy elements, the carbon, oxygen, iron, and silicon, forged in the nuclear furnaces of those massive stars and scattered by their supernova death. This process is how the pristine hydrogen and helium left over from the Big Bang becomes seeded with the elements necessary for planets and ultimately life. Before these galactic winds, the vast voids between galaxies were a virtual desert, barren of these complex elements. These outflows act as cosmic distributors, shipping enriched material far and wide, ensuring that when the next generation of galaxies forms, perhaps billions of years later and from different material, it will already be pre-salted with the ingredients for rocky worlds. This grand cycle connects the violent death of stars in one galaxy to the potential for life in another, highlighting a profound interdependence that links all galaxies across the tapestry of space and time. And yet, for all we have uncovered about the grand story of galaxies, from their quantum beginnings to their collisional endings, the most thrilling chapter may be the one we are about to write. Our current understanding is a magnificent tapestry, but it is woven with threads of inference and dotted with lingering mysteries. The true nature of dark matter and dark energy, the detailed physics of the very first stars, the precise mechanisms that govern black hole feedback, these are the frontiers of our knowledge. But we are not at an endpoint. We are on the verge of a new golden age of observation, an era where our cosmic vision will extend further and see clearer than ever before, thanks to a new generation of telescopes that are nothing short of miraculous. Leading this charge is the James Webb Space Telescope, an instrument that has already begun to fundamentally reshape our view of the early universe. Unlike Hubble, which primarily sees invisible and ultraviolet light, Webb is an infrared telescope, and this gives it a profound superpower for cosmic time travel. Because the universe is expanding, the light from the most distant, ancient galaxies is stretched into the infrared part of the spectrum by the time it reaches us. Webb is uniquely designed to collect this faint, redshifted glow. It's like having a new set of eyes that can see in a color the universe has been using to write its oldest stories. Already, it is peering back to within a few 100 million years of the Big Bang, spotting galaxies that are far more massive and structured than our models predicted. These observations are not just breaking records, they are breaking our theories, forcing a thrilling and rapid reevaluation of how quickly the first galaxies could assemble themselves from the primordial darkness. Every new deep field image from Webb is a direct look back at the era of first light, a chance to witness the epoch of reionization happening in real time across the cosmos. But Webb is just the beginning. Here on Earth, a new class of behemoths is rising. The extremely large telescopes, or ELT, including the giant Magellan telescope and the 30-meter telescope, are poised to revolutionize our view from the ground. With mirrors nearly 100 meters across, these are not just incremental improvements. They are quantum leaps in light-gathering power and resolution. Their primary weapon is a technology called adaptive optics, which uses powerful lasers to create artificial guide stars in the upper atmosphere, measuring the blurring effect of our air and then deforming the telescope's mirrors thousands of times a second to cancel it out. The result will be images from the surface of the Earth that are sharper than anything Hubble could ever produce. the implications for galactic studies are staggering. We will be able to resolve individual stars in the halos of galaxies far beyond our local group, mapping their movements and chemistries in exquisite detail. We will watch supermassive black holes at the hearts of distant galaxies flare and flicker, studying the accretion process in real time. We might even directly image terrestrial planets orbiting within the habitable zones of nearby stars, searching for the atmospheric biosignatures that would hint at life. The ALTs will turn the distant cosmos into our nearby neighborhood, and then there is the radio universe, which will be unveiled by a project of almost unimaginable scale, the Square Kilometre Array. The SKA won't be a single dish, but a vast network of thousands of radio antennae spread across 2 continents, in South Africa and Australia, working in perfect synchrony to create a virtual telescope with a collecting area of, as the name suggests, a square kilometre. Its sensitivity will be so profound that it could detect an airport radar on a planet tens of light years away. For galaxy formation, its most revolutionary role will be mapping the cosmic web during the Dark Ages before the first stars ever switched on. It will do this by detecting the faint radio signature of neutral hydrogen gas, the raw material of galaxies. The SKA will create 3-dimensional maps of this gas throughout the entire early universe, revealing the invisible scaffolding of dark matter upon which it condensed. It will watch as the first stars and galaxies ignite and begin to ionize this hydrogen, charting the process of reionization in a way Webb can only hint at. Furthermore, by tracking the rotation of billions of galaxies across cosmic time, the SKA will allow us to create the most precise charts of the universe's expansion ever made, potentially revealing the exact nature of dark energy and whether its strength has changed over the life of the cosmos. Together, these instruments represent a new sensory system for humanity, each complementing the other. Webb sees the first starlight, the ELTs will dissect it with unparalleled clarity, and the SKA will map the dark matter canvas upon which it is painted. We are no longer merely observers of the cosmic story. We are becoming active participants in its decoding. The mysteries that have captivated us for generations, the identity of dark matter, the force of dark energy, the ignition of the first dawn, are no longer locked away in the distant past. They are now targets in the crosshairs of our technology, waiting to be revealed by the next photon of ancient light, the next whisper of radio noise that journeys across the universe to finally reach our waiting machines and our wondering minds. So as we bring our journey through these 30 facts to a close, what ultimately emerges is a picture that completely shatters the old, static view of the cosmos. Galaxies are not simply immutable islands of light frozen in the void. They are dynamic, evolving characters in the grandest story ever told. They are born from the faintest quantum whispers. They grow through violent mergers and serene accretion. They are regulated by the furious feedback from their central black holes, and they eventually fade or transform, their destinies written as much by their cosmic environment as by their own internal nature. This narrative reveals a universe that is profoundly interconnected, where the death of a single massive star in a stellar nursery can seed future worlds with the elements for life, and where the invisible tug of dark matter from a passing galaxy can dictate the fate of another billions of years later. Our understanding of this magnificent saga is not a closed book. It is a living, breathing field of science, constantly being rewritten with every new observation from telescopes like James Webb and every new simulation on a supercomputer. The mysteries of dark matter and dark energy, the details of the very first starlight, the intricate mechanics of black hole feedback, these are the frontiers we are actively exploring. Each discovery peels back another layer, revealing a cosmos that is more complex, more violent, and more beautiful than we ever could have imagined just a generation ago. This means that the next time you find yourself under a clear, dark sky, far from the city lights, take a moment to truly look up. That faint, hazy band of the Milky Way is no longer just a beautiful smear of stars. It is a living, breathing entity. It is a cannibal currently digesting a smaller galaxy. It is a recycler, fountaining material from dying stars back into its disk to birth new ones. It is a historical record with streams of stars telling tales of ancient collisions, and it is on a collision course with its giant neighbor, Andromeda, in a dance that will one day reshape them both. Every point of light you see is part of this story. You are not just looking at a static picture, you are witnessing a single frame in a billion-year-long movie of creation and destruction. You are seeing the cosmic tapestry not as a finished product, but as a work in progress, and you are here, right now, with the privilege to understand just a little bit of its magnificent, unfolding story.